Tonight, we're going to talk about a planet that was once celebrated as the closest thing to a second Earth ever discovered, a world that captured the imagination of scientists and the public alike, and a story that quietly turned into something very different from what the headlines first suggested. In April of 2014, NASA announced the discovery of Kepler 186f, a planet roughly the size of our own, orbiting in the habitable zone of a distant star nearly 500 light-years away. For the first time in human history, we had found a rocky world that could plausibly have liquid water on its surface, circling another sun. Earth's twin, the press called it, a mirror of our own planet, sitting in a quiet corner of the constellation Cygnus. But then, slowly, as the years passed and more careful work was done, the picture began to shift. The deeper astronomers looked, the less the planet resembled the world we had been told about. The temperature was wrong. The light was wrong. The host star was wrong in ways that mattered far more than anyone wanted to admit at the time of the announcement. And by the end of tonight, you're going to understand why Kepler 186f, the planet that was supposed to be our cosmic sibling, may in fact be one of the most cautionary tales in the entire history of exoplanet science. A story about how badly we wanted to find ourselves out there, and what happened when the universe gently, almost apologetically, refused to cooperate. Before we get started, if you love exploring the strangest corners of the cosmos as much as we do, take a moment to like the video or subscribe to the channel. It's a small thing, but it helps stories like this one reach more people who think the way you do. Now, let's begin. To understand why the announcement of Kepler 186f mattered so much, you have to understand what came before it. For most of human history, the question of whether other worlds existed around other stars was a matter of pure philosophy. Ancient Greek thinkers debated it. Renaissance astronomers speculated about it. Giordano Bruno was burned at the stake in 1600 partly for insisting that the stars in the night sky were other suns with their own planets and their own inhabitants. But for centuries afterward, no one could actually prove it one way or the other. The technology simply did not exist. Stars were points of light, and whatever orbited them, if anything orbited them at all, was hidden in the glare. That changed in 1995, when Michel Mayor and Didier Queloz, two Swiss astronomers working at the Haute-Provence Observatory in France, detected the first confirmed planet orbiting a sun-like star. It was called 51 Pegasi b, and it was nothing like anyone had expected. A gas giant the size of Jupiter, but orbiting so close to its star that its year lasted only about 4 Earth days. The surface temperature was hot enough to melt lead. It bore no resemblance whatsoever to anything in our own solar system. And yet, in a strange way, that was the point. 51 Pegasi b proved that planets around other stars were not just possible. They were real. They were findable. The galaxy was not empty. In the years that followed, the floodgates opened. Hundreds, then thousands of exoplanets were discovered using increasingly sophisticated techniques. Most of them were like 51 Pegasi b, large planets close to their stars, easy to detect because they tugged on their stars hard enough to make them wobble in measurable ways. Smaller planets, planets like Earth, remained beyond the reach of those early instruments. They were too small, too distant, too quiet to make their presence known. That was where the Kepler Space Telescope came in. Launched in March of 2009, Kepler was designed for one purpose, and one purpose only. It was built to find Earth. Not our Earth, of course, but another one. A small rocky planet orbiting a sun-like star at the right distance for liquid water to exist on its surface. The telescope was placed in an orbit around the Sun, trailing behind our own planet, and it spent 4 years staring at a single patch of sky in the constellation Cygnus, watching more than 150,000 stars at once, looking for the faint, periodic dimming that occurs when a planet passes in front of its star. A transit, as astronomers call it. The dimming is tiny, sometimes only a few parts in 10,000, but Kepler was sensitive enough to catch it. For years, the mission delivered planet after planet. Some were strange, some were enormous, some were so close to their stars that they should not, by any reasonable theory, have been able to form there at all. But the planet everyone really wanted, the one Kepler had been built to find, remained elusive. The truly Earth-sized worlds in the habitable zones of their stars stubbornly refused to appear in the data. The mission scientists searched and searched, and every time they thought they had found one, closer examination revealed it was a little too big, or a little too close to its star, or orbiting a star a little too different from our sun to count. And then, in the spring of 2014, after 5 years of careful work, the announcement came. Kepler 186f, a planet roughly 1.1 times the size of Earth, orbiting in the habitable zone of its star. The first confirmed Earth-sized world in the right place for liquid water. The press conference was electric. Headlines around the world declared the discovery of Earth's twin, the closest thing to a second home humanity had ever found. Scientists who had spent their careers searching for exactly this moment spoke with visible emotion. For one brief, glorious week, it seemed as though everything the field had been working toward for 2 decades had finally been delivered. We were no longer alone. We had a sibling out there in the dark. But there was already, even at that early stage, something the announcement was not quite telling you. Something that was technically mentioned in the scientific papers, but quietly downplayed in the press materials. Something about the star Kepler 186f was orbiting, and about the kind of light it was receiving, and about what that light would actually do to a planet sitting at the precise distance the press releases were celebrating. The story being told to the public was a story of triumph. The story being told in the journals, when you read them carefully, was already a little more uncertain. And in the years that followed, that uncertainty would only grow, until what had started as the discovery of Earth's twin had quietly become something stranger, colder, and far less hospitable than anyone had originally let on. The story of Kepler 186f does not really begin in 2014 with the press conference and the headlines. It begins much earlier, in the mind of a single astronomer named William Borucki, who spent more than 2 decades of his life trying to convince anyone at NASA to take him seriously. Borucki, working out of the Ames Research Center in California, had become obsessed in the 1980s with a deceptively simple idea. If a planet passed directly between us and its star, the star would briefly dim, not by much. A planet the size of Earth crossing a star the size of our Sun would block only about 1/10,000th of the star's light. But that dimming, if you could measure it precisely enough, would be a signature, a fingerprint, a way to find planets you could never hope to see directly. The problem was that no instrument on Earth could measure starlight that precisely. The atmosphere itself shimmered too much. Telescopes on the ground were good for many things, but not for detecting changes of 1 part in 10,000 in the brightness of a faint, distant star. To do that, you needed to put a dedicated photometer in space, far from the distortions of weather and air, and you needed to point it at the same patch of sky for years on end, without looking away. Borucki proposed exactly this mission to NASA in 1992. He was rejected. He proposed it again in 1994. Rejected. He proposed it in 1996, again in 1998, and again in 2000. Each time, the review panels found reasons to say no. The technology was unproven. The science was speculative. The cost was high. The chances of success were uncertain. By the late 1990s, Borucki had become something of a quiet figure in the planetary science community, a man chasing a dream that most of his colleagues had politely concluded was probably impossible. What finally changed things was not a sudden breakthrough, but a slow accumulation of evidence. The Hubble Space Telescope demonstrated that ultra-precise photometry was achievable from orbit. Ground-based teams began detecting transits of giant planets, proving the basic concept worked. And as the count of confirmed exoplanets climbed past 100, then past 200, the scientific community began to accept that planets around other stars were not just real, but staggeringly common. The question was no longer whether they existed, but what kinds existed and where. In 2001, NASA finally selected Borucki's proposal. It was given the name Kepler, after the 17th century German astronomer Johannes Kepler, who had formulated the laws of planetary motion. After 8 more years of design, construction and testing, the spacecraft launched on the 6th of March, 2009 on a Delta II rocket from Cape Canaveral. The instrument itself was a marvel of focused engineering. It was essentially a single enormous camera, 95 megapixels in size, attached to a telescope with a mirror about 1.5 meters across. It was placed not in orbit around Earth, but in orbit around the Sun, trailing slowly behind our own planet at a distance that would steadily increase over the years. This was deliberate. Earth itself would have been a source of interference, with its reflected light and its gravitational tugs on the spacecraft. Out in solar orbit, Kepler could stare at one fixed point in the sky without ever being interrupted. The target field was a small region in the constellation Cygnus, chosen because it lay just above the plane of the Milky Way, dense with stars but free of obstructive dust. From its lonely vantage point, Kepler watched 150,000 stars at the same time, recording the brightness of each one every 30 minutes, year after year after year. In 2010, the first results began to appear. Hot Jupiters, mostly. The same kinds of strange giant planets that ground-based surveys had been finding for years. But as the data accumulated and the analysis techniques improved, smaller and smaller planets began to emerge from the noise. By 2011, Kepler had found planets the size of Neptune. By 2012, planets the size of Earth, though most of them were too close to their stars to be of much interest for the habitable zone question. By 2013, the catalogue of candidate planets had ballooned into the thousands, and entire teams of astronomers were working full-time just to verify which ones were real and which ones were false positives. One of those teams was led by a young astronomer named Elissa Quintana, working at the SETI Institute in California. Quintana and her colleagues had been studying a particular star in the Kepler field, a small, dim, reddish star catalogued as Kepler 186. It was nothing remarkable to look at. About half the size of our Sun, far cooler, far less luminous, the kind of star that would never be visible to the naked eye, even though it sat only about 500 light-years away from us. In the grand scheme of stellar populations, it was one of the most common types of star in the galaxy. Astronomers call them M-dwarfs, or red dwarfs, and they outnumber Sun-like stars by roughly 4 to 1. Most of the stars in the Milky Way are stars like Kepler 186. By early 2014, the team already knew that this little red dwarf had at least 4 planets. Kepler 186b, C, D, and E, all small, all rocky, all huddled close to the star in tight, fast orbits. None of them was in the habitable zone. They were all too hot, blasted by their star's radiation, with surface temperatures that would make Mercury look comfortable. But as Quintana's team continued to process the data, they began to notice something else. A fainter signal, much harder to detect, with a much longer period. Every 130 days or so, the star dimmed by a tiny amount, and the pattern repeated with the regularity of clockwork. A 5th planet, farther out, in a colder, slower orbit, sitting, as the calculations soon revealed, at exactly the right distance from its star for liquid water to potentially exist on its surface. They called it Kepler 186 if the verification process took months. The team needed to rule out every possible source of false signal. Background stars contaminating the photometry, stellar activity mimicking a transit, instrumental artifacts in the spacecraft. They cross-checked the Kepler data against ground-based observations from the W.M. Keck Observatory in Hawaii and the Gemini Observatory in Chile. They modeled the star's properties using high-resolution spectroscopy. They eliminated possibility after possibility until what remained was unmistakable. A planet roughly 1.1 times the size of Earth, with an orbital period of 130 days, circling a star where, on paper at least, the conditions for liquid water seemed to be satisfied. That was the moment when the discovery moved from being a piece of careful scientific work to being a global story. NASA scheduled a press conference. Reporters were briefed. The phrase Earth's twin began to appear in internal communications, and then in headlines, and then in conversations around dinner tables. What no one was emphasizing yet, what would only become clear later, was that the star at the center of this story was not a star like our Sun at all. And that fact, more than any other, would eventually unravel everything the public thought it knew about the planet called Earth's twin. To understand why the announcement of Kepler 186f hit the scientific community the way it did, you have to understand what the prevailing wisdom about habitability looked like in the years leading up to the discovery. Because the field had been quietly building a framework for decades, a kind of unspoken consensus about what kinds of planets, around what kinds of stars, were the right places to look for a second Earth. And that framework, as it turned out, was about to be tested in ways no one had quite anticipated. The central concept in habitability research, the one every astronomer working in the field could recite in their sleep, is something called the habitable zone. The term was popularized in the 1950s by an astronomer named Hubertus Strughold, and it refers to the range of distances from a star within which a rocky planet could plausibly maintain liquid water on its surface. Too close and the water boils away. Too far and it freezes solid. The habitable zone is sometimes called the Goldilocks zone for exactly this reason. Not too hot, not too cold, just right. In our own solar system, the habitable zone extends roughly from the orbit of Venus to the orbit of Mars, with Earth sitting comfortably in the middle. The boundaries are not sharp. They depend on assumptions about atmospheric composition, cloud cover, and the reflective properties of the planet's surface. But the basic idea has held up well, and for most of the modern history of exoplanet science, the habitable zone has been the single most important criterion for judging whether a newly discovered world might be capable of supporting life. For a long time, the assumption was that you wanted to look for habitable zone planets around stars like our own. Yellow dwarfs, technically classified as G-type stars, with masses, temperatures, and lifetimes similar to the Sun. There were good reasons for this. Our Sun had produced a planet with life on it, so by the most obvious logic, stars like our Sun seemed like the natural place to look for other planets with life on them. The Sun was stable. Its energy output varied by only a fraction of a percent over the course of its 11-year activity cycle. It had been shining steadily for 4.5 billion years, providing the long, calm baseline conditions that life on Earth had needed to develop from single-celled organisms into the complex biosphere we know today. Other G-type stars, the reasoning went, should be capable of doing the same thing. The problem with this assumption, the problem that began to surface in the late 1990s and early 2000s, was that G-type stars are rare. Only about 7% of the stars in the Milky Way are Sun-like. The vast majority of stars in the galaxy, somewhere between 70 and 80% of them, are M-dwarfs. The small, cool, reddish stars that astronomers had historically overlooked because they were so dim and so unspectacular. If you wanted to find habitable planets in significant numbers, you could not afford to ignore M-dwarfs. There were simply too many of them, and too few Sun-like stars in comparison, to make a survey of only G-type stars practical. So in the late 1990s, a growing number of astronomers began to ask a question that would have seemed almost heretical a generation earlier. What if M-dwarfs could also host habitable worlds? Could the habitable zone of a small, cool, red star also be a place where life could arise? On paper, the answer seemed to be a cautious yes. You would simply need to move closer to the star to find the right temperature range. The habitable zone of an M-dwarf is much closer in than the habitable zone of a star like the Sun, sometimes just a few million miles from the stellar surface, because M-dwarfs produce so much less energy. But the basic geometry worked. There was a region around every M-dwarf where, in principle, liquid water could exist on the surface of a rocky planet. And given how many M-dwarfs there were, the total number of habitable real estate slots in the galaxy might be staggering. Some estimates suggested that there could be tens of billions of such planets in the Milky Way alone. This was the intellectual environment into which the Kepler mission had been launched. The hunt was for Earth-sized planets in habitable zones, and while the original framing of the mission had emphasized Sun-like stars, the discovery of so many M-dwarf planets in the Kepler data quickly shifted the conversation. By 2012, papers were being published that explicitly identified M-dwarfs as the most promising targets for habitable planet searches, simply because the planets were easier to find. The transit signal of an Earth-sized planet crossing a small red dwarf is much deeper than the same planet crossing a sun-like star, because the planet blocks a larger fraction of the star's total light. The orbital periods are shorter, meaning you could confirm a planet's existence in months instead of years. And the planets themselves, being closer to their stars, tugged on them harder, making follow-up confirmation through radial velocity easier as well. Everything about M-dwarfs from a detection standpoint was attractive, but there was a counter-argument, and it had been growing louder throughout the 2000s and into the early 2010s. The counter-argument was that M-dwarfs, despite their apparent abundance, might be terrible places for life. The reasons were technical, but they were also serious. M-dwarfs are dramatically more active than stars like our Sun. They produce frequent and powerful flares. They emit far more of their energy in the ultraviolet and X-ray portions of the spectrum, wavelengths that are highly damaging to biological molecules and atmospheric chemistry. Their habitable zones are so close to the star that any planet in them would almost certainly be tidally locked, meaning the same hemisphere would face the star permanently, while the opposite hemisphere lay in permanent darkness. And M-dwarfs, when they are young, go through a phase lasting hundreds of millions of years, during which they are so violently energetic that any nearby planet's atmosphere could be stripped away entirely before life ever had a chance to begin. These were not minor concerns. They were, in fact, the central debate in habitability research throughout the early 2010s. Two camps had formed, sometimes called the optimists and the pessimists. The optimists argued that M-dwarf planets could find ways to retain their atmospheres, develop magnetic fields, redistribute heat from their day sides to their night sides through atmospheric circulation, and ultimately produce environments where life could survive and even thrive. The pessimists argued that the sheer hostility of the M-dwarf environment, the constant bombardment of high-energy radiation, the lack of a day-night cycle, the tidal forces, the catastrophic early phase of stellar activity, made it nearly impossible for any planet in such a habitable zone to actually be habitable in any meaningful sense. When Kepler 186f was announced, the press materials and most of the public coverage emphasized the optimist view. The planet was in the habitable zone. It was roughly the size of Earth. The conditions, on paper, were right for liquid water. Everything else was secondary. But within the scientific community, the same announcement was being received with a much more complicated reaction. Because if Kepler 186f really was Earth's twin, then everything the pessimists had been warning about for the previous decade was about to be tested in the real world. And the answers, when they came, would not be the ones anyone in the public-facing parts of the field had been hoping for. The first cracks in the Earth's twin narrative did not appear in a single dramatic moment. There was no press conference where someone stood up and said, "Actually, we were wrong. This planet is nothing like our own." Instead, the doubts emerged the way most scientific doubts emerge, slowly, through technical papers, through quiet conversations at conferences, through follow-up observations that produced results just slightly different from what the original announcement had implied. If you were not paying close attention to the exoplanet literature in the months and years after April 2014, you might have missed the shift entirely. The public narrative remained intact. The phrase Earth's twin continued to appear in articles and television specials and educational documentaries. But within the community of researchers who actually studied the planet, something else was happening. A quiet recalibration. A slow, deliberate walking back of the most exciting claims. The first issue was the most fundamental. It had to do with how the size of the planet had been determined in the first place. When Kepler detects a transit, what it actually measures is the depth of the dimming, expressed as a fraction of the star's total light. From that number, combined with an estimate of the star's size, you can calculate the size of the planet. The arithmetic is straightforward. The planet's area is the same fraction of the star's area as the dimming is of the total brightness. But the calculation has a vulnerability. If your estimate of the star's size is wrong, your estimate of the planet's size is wrong too, and by the same proportion. A star that turns out to be 10% larger than originally thought produces a planet that is 10% larger than originally thought. In the case of Kepler 186, the star itself was something of an unknown quantity at the time of the discovery. It was small, dim, and far away. Determining the precise radius of a star 500 light-years from Earth is not a trivial task, and the early measurements relied on a combination of spectroscopic analysis and stellar models, both of which carried significant uncertainties. The original paper had estimated the planet's radius at about 1.11 times the radius of Earth, with error bars that gave a range from roughly 1.04 to 1.18 Earth radii. That was small enough to be confidently classified as a rocky world. Above about 1.5 Earth radii, planets start to accumulate thick hydrogen atmospheres and look more like miniature Neptunes. Below that threshold, they tend to remain solid, with surfaces and oceans and the possibility of geology resembling our own. Kepler 186f, with its modest estimated size, sat comfortably in the rocky planet category. But over the following years, as the star itself was studied more carefully, the estimates of its properties drifted. New high-resolution spectroscopic surveys produced slightly different values for its temperature, its metallicity, its luminosity. The stellar models used to interpret these measurements were themselves being refined, particularly for M-dwarfs, which had historically been one of the most poorly understood categories of stars. By the late 2010s, the best estimates of the planet's size had shifted slightly, sometimes up, sometimes down, but always within a range that left the planet identifiable as roughly Earth-sized. This was not, in itself, a problem. The planet was still small. It was still rocky, but the uncertainty surrounding even this most basic property hinted at a larger issue. The further you looked, the more the precision of the original announcement gave way to something fuzzier and harder to pin down. The second crack was more serious, and it had to do with the planet's position within the habitable zone. The original announcement had placed Kepler 186f in the habitable zone of its star, but it had not been particularly specific about where in the habitable zone. The habitable zone is not a single sharp line. It has an inner edge and an outer edge, and the distance between them depends on a number of assumptions about the planet's atmosphere. The most common definition, called the conservative habitable zone, assumes a planet with a moderate carbon dioxide atmosphere similar to a young Earth. A more generous definition, called the optimistic habitable zone, allows for thicker atmospheres and stronger greenhouse warming, expanding the boundaries outward. When the team that announced Kepler 186f did the math, they found that the planet sat near the outer edge of the conservative habitable zone, not in the middle, not in the warm, comfortable region where Earth itself orbits the Sun. Near the edge, where conditions are colder, where the energy received from the star is dramatically less, where any atmosphere would have to do significant heavy lifting to keep the surface temperature above the freezing point of water. How much less energy? The numbers were uncomfortable. Kepler 186f receives roughly 32% of the solar flux that Earth receives, less than a third. That is closer, in terms of incoming energy, to the orbit of Mars than to the orbit of Earth. And Mars, as anyone who has looked at it through a telescope knows, is a frozen desert with a thin atmosphere, an average surface temperature of about -60 degrees Celsius, and no liquid water of any kind on its surface today. The reason Mars is cold is not complicated. It is too far from the Sun. It receives only about 44% of Earth's solar flux, and that is already too little to maintain habitable conditions without significant atmospheric warming. Kepler 186f receives even less energy than Mars. On the most basic, first principles calculation, with no atmosphere and only the star's energy to keep the surface warm, the equilibrium temperature of Kepler 186f would be around -80 degrees Celsius. Frozen solid, encased in ice, about as far from the gentle, temperate conditions of Earth as it is possible to imagine while still technically remaining inside the habitable zone. To produce liquid water on its surface, the planet would need a substantial atmosphere capable of trapping heat through the greenhouse effect, far more substantial than Earth's atmosphere is today. Without such an atmosphere, Kepler 186f is not Earth's twin. It is something closer to a slightly larger, slightly colder version of Mars. This was the second crack. The planet's position in the habitable zone was real in the strictly technical sense, but it was a marginal position. It depended on assumptions about the atmosphere that no one could actually verify, and the assumptions that would make the planet warm enough to be habitable were not modest. They required a planet substantially different from Earth in terms of atmospheric composition, with much more carbon dioxide, possibly augmented by other greenhouse gases, in concentrations that would have made the air toxic to anything resembling life as we know it. None of this was hidden in the original paper. The scientists who announced the discovery were careful, and they noted these caveats explicitly. But the caveats were buried in technical sections that almost no one in the general public read, while the headlines focused exclusively on the parts of the story that made the planet sound exciting. And the third crack, when it came, was the one that would prove most damaging of all. It was not about the planet itself. It was about the star. Before we can talk about what was wrong with the star, and what made it such a problem for the habitability of Kepler 186f, we have to talk about how we know anything about distant stars at all. Because the entire edifice of modern exoplanet science rests on a foundation of stellar characterization, and that foundation is built from a handful of remarkably clever techniques developed over the past century and a half. Understanding how those techniques work is essential to understanding why the announcement of Earth's twin was always going to be more complicated than the headlines suggested. The most basic tool in stellar astronomy is the spectrum. When you pass starlight through a prism or a diffraction grating, the light spreads out into a rainbow of colors, and superimposed on that rainbow are thousands of dark lines. These lines are called absorption lines, and they form because specific atoms and molecules in the star's outer layers absorb specific wavelengths of light as it travels outward from the stellar interior. Hydrogen has its own characteristic set of lines. Helium has another. Iron, calcium, sodium, titanium oxide, water vapor, each element and molecule in the star's atmosphere leaves a unique fingerprint in the spectrum. By examining where the lines fall and how strong they are, astronomers can determine an extraordinary amount about a star without ever leaving Earth. Its temperature, its surface gravity, its chemical composition, its rotation rate, its motion through space, all encoded in the patterns of light and shadow in the spectrum. This technique, called spectroscopy, was developed in the 1860s by a German physicist named Gustav Kirchhoff and a chemist named Robert Bunsen, working together in Heidelberg. Their fundamental insight, that the chemical composition of a distant object could be determined purely from the light it emitted, was so revolutionary that the French philosopher Auguste Comte had declared, only a few decades earlier, that humanity would never know what the stars were made of. He was wrong by exactly one generation. By the time of his death, spectroscopy was already revealing the composition of the sun, and within 100 years it had become the standard method for studying every star in the sky. For a star as small and dim as Kepler 186, getting a good spectrum is challenging, but not impossible. The original team had used the Keck Observatory in Hawaii with its 10-meter telescopes, and the Gemini North Observatory, also in Hawaii, with its 8-meter telescope, to obtain detailed spectra of the star. From those spectra, they were able to determine its temperature, approximately 3,750 Kelvin, which is about 2,000 degrees cooler than the sun. They determined its surface gravity, which is roughly 4.5 times Earth's gravity at the photosphere, consistent with a dwarf star rather than a giant. They determined its metallicity, the fraction of elements heavier than hydrogen and helium, and found it to be slightly lower than the sun's. And they determined its rotation rate, which turned out to be slow, on the order of 34 days for a single revolution, suggesting an older star past the violent activity phase of its youth. All of this information went into the calculation of the star's age, which the team estimated at about 4 billion years. That number was important. A planet orbiting a 4 billion-year-old star has had plenty of time to develop whatever conditions it is ever going to develop. If life can arise on it, it has had the time to do so. If the atmosphere has been stable for that long, it is likely to remain stable into the future. 4 billion years is comparable to the age of our own solar system, and it is the kind of timescale that makes habitability seem plausible rather than merely possible. But here is where the second technique enters the story, and where the picture began to grow more complicated. Because spectroscopy can tell you what a star is doing right now, in the present moment, it cannot, on its own, tell you what the star was doing 4 billion years ago, when whatever planets orbit it were first forming. For that, you need to look at other stars of the same type at different ages, and you need to build models of how stars like the one you are studying evolve over time. And the models for M-dwarfs, in the years following the Kepler 186 announcement, were becoming a source of increasing alarm. The reason was something called the pre-main sequence phase. Every star, when it first forms from a collapsing cloud of gas and dust, goes through a period of intense activity before it settles into the steady, hydrogen-burning state that defines most of its life. For sun-like stars, this phase lasts about 50 million years. It is energetic, but it is brief compared to the star's total lifetime of 10 billion years or so. By the time Earth had finished forming, the sun had already calmed down into its current quiet behavior. But for M-dwarfs, the pre-main sequence phase is dramatically longer. Depending on the specific mass of the star, it can last anywhere from a few 100 million years to more than 1 billion years. During that entire stretch of time, the young M-dwarf is significantly more luminous than it will be later in its life, and far more active. It produces enormous flares, sometimes increasing its total energy output by factors of 100 or more in a matter of minutes. It emits intense ultraviolet and X-ray radiation. It blasts charged particles outward in violent stellar winds. For any planet caught in the habitable zone of a young M-dwarf, this prolonged early phase is catastrophic. The habitable zone, remember, is the region where liquid water can exist on the surface based on the present-day energy output of the star. But during the pre-main sequence phase, when the M-dwarf is much brighter, the habitable zone is much further out. The region that will eventually become habitable billions of years later sits inside the much hotter early habitable zone for the first several 100 million years of the system's life. Anything in that region during the early phase would be subject to extreme heating, intense ultraviolet bombardment, and powerful stellar wind erosion. The atmosphere of such a planet would be stripped away. Any water on the surface would evaporate and then be lost to space through a process called hydrodynamic escape, where hydrogen atoms freed by the breakdown of water molecules in the upper atmosphere are blown into interplanetary space by the stellar wind. By the time the star finally calms down and the present-day habitable zone becomes a place where liquid water could theoretically exist again, the planet that occupies that zone has already been baked, dried, and stripped of most of its atmosphere. This was the third crack, and it was the deepest one. Because Kepler 186, like all M-dwarfs, would have gone through exactly this kind of prolonged violent youth. The current age of the star, 4 billion years, told you nothing about what conditions had been like during the first 800 million years of its existence. And in those first 800 million years, any rocky planet sitting in what would eventually become the conservative habitable zone, which is exactly where Kepler 186f sits, would have been subjected to conditions that would have made the surface of Venus look gentle by comparison. The window during which the planet might have been habitable in the conventional sense, if such a window existed at all, did not begin at the moment of formation. It began only after the star had finished its long, destructive infancy. And whether anything resembling a planetary atmosphere could have survived that infancy was a question that, in the years following the original announcement, would receive an answer no one in the public-facing parts of the field really wanted to hear. The first major piece of evidence that something was deeply wrong with the standard picture of M-dwarf habitability did not come from Kepler 186 itself. It came from a different star, much closer to home, in a study published in the summer of 2017 by a team of researchers working primarily at the Goddard Space Flight Center in Maryland. The star was Proxima Centauri, our nearest stellar neighbor, and the study focused on a planet called Proxima b, which had been discovered the previous year and which, like Kepler 186f, sat squarely in its star's habitable zone. The researchers were trying to answer a deceptively simple question. Could the atmosphere of a planet around an M-dwarf survive the stellar wind? To find out, they had used data from NASA's Mars Atmosphere and Volatile Evolution mission, known as MAVEN, which had been orbiting Mars since 2014, and which had been specifically designed to measure how the Martian atmosphere was being lost to space. Mars, as the mission had confirmed, is in the process of losing about 100 grams of atmosphere per second to the solar wind, a slow but relentless leak that has been going on for billions of years, and that has stripped the planet of most of the dense, protective envelope it once possessed. The reason Mars is so vulnerable, the reason it has lost so much, is that it lacks a global magnetic field. Without a magnetosphere to deflect the charged particles streaming outward from the sun, the solar wind reaches the upper atmosphere directly, where it ionizes molecules and accelerates them to escape velocity. Earth, by contrast, retains its atmosphere in part because our planet's magnetic field acts as a shield, deflecting the solar wind around us like water flowing around a stone in a river. The Goddard team took the MAVEN data, which described atmospheric loss rates under the conditions produced by our sun's relatively gentle stellar wind, and scaled them up to the conditions that would prevail around Proxima Centauri, which is far more active. The results were brutal. Under the bombardment of Proxima Centauri's stellar wind, an Earth-like atmosphere on Proxima b would be stripped away in a few 100 million years at most, possibly in less than 100 million years. The planet would be left with essentially no atmosphere at all, a bare rocky surface exposed to vacuum and radiation, with any water that had once existed lost to space long ago. This finding sent a chill through the exoplanet community, because Proxima Centauri, while older and somewhat less active than the youngest M-dwarfs, is in many respects a fairly typical example of the kind of star around which most habitable zone planets are being discovered. If Proxima b could not retain an atmosphere, what hope was there for other M-dwarf planets? And what did this mean specifically for Kepler 186f, which orbits a star of similar mass and similar type, and which sits in a habitable zone that is similarly close to its star? The implications were not lost on the researchers studying Kepler 186f. Within a year of the Proxima study, several papers had appeared examining the atmospheric loss problem in the context of M-dwarf habitable zone planets more generally. The conclusions, while couched in the careful language of scientific uncertainty, were difficult to read in any way that was favorable to the Earth's twin narrative. The pre-main sequence phase of Kepler 186, the team estimated, would have lasted somewhere between 500 million and 1 billion years. During that time, the star's ultraviolet output would have been roughly 100 times what it is today. Its X-ray output would have been several hundred times current values. Its stellar wind would have been correspondingly more intense. Any atmosphere on Kepler 186f during that early phase would have been subjected to erosion rates dramatically higher than what Mars is currently experiencing, and dramatically higher than what Proxima b would be experiencing today. The math was not encouraging. If Kepler 186f had started its life with an atmosphere roughly the mass of Earth's, the early stellar bombardment would likely have stripped most of it away within a few 100 million years. Even if the planet had managed to retain some residual atmosphere through later outgassing from volcanic activity, the dense, warm, greenhouse-rich envelope it would need to maintain liquid water at its current orbital distance, with only 32% of Earth's solar flux, would have been almost impossible to sustain over geological time. The planet today, the researchers were forced to conclude, was most likely a frozen, airless or near-airless world, with whatever water it might once have possessed locked permanently in ice or lost entirely to space. This was not, however, the kind of finding that made global headlines. It appeared in journals like the Astrophysical Journal and Astronomy and Astrophysics, in papers with titles dense with technical jargon, read mostly by other researchers in the field. The press cycle that had elevated Kepler 186f to the status of Earth's twin had moved on by then. The discovery was 3 years old. There were newer, more exciting planets to write about. The slow accumulation of evidence that the original framing had been over-optimistic did not make for a compelling news story, and so it was largely ignored by the outlets that had originally celebrated the announcement. But within the scientific community, the reaction was more nuanced. Some researchers, the more pessimistic ones, took the new findings as confirmation of what they had been warning about for years. M-dwarf habitable zones, they argued, were probably not habitable at all in any practical sense. The conditions were simply too hostile. The early stellar activity was too violent, the long-term stellar wind too erosive, the lack of a thick atmosphere too damaging. If you wanted to find life, you needed to look at G-type stars, even if there were fewer of them. Other researchers, the more optimistic ones, pushed back. There were possible escape routes from this dilemma, they argued. A planet with a strong magnetic field might be able to deflect the stellar wind. A planet with sufficient initial water content might be able to replenish its atmosphere through volcanic outgassing faster than it was being lost to space. A planet with a thick early carbon dioxide atmosphere might be able to survive the pre-main sequence phase long enough for the star to settle into its quieter middle age. The pessimists, they said, were ignoring the possibilities. The pessimists, in turn, accused the optimists of grasping at straws. This debate, which continues in some form to this day, played out in conferences and journals, and increasingly on social media, where exoplanet astronomers had begun to congregate on platforms like Twitter to argue about the latest results. The arguments were technical, often involving detailed atmospheric models, complex chemistry, and assumptions about planetary interior structure that no one could actually verify. But underneath the technical arguments was a deeper philosophical question, one that the discovery of Kepler 186f had brought into sharp relief. What were we actually looking for when we were looking for habitable planets? Was it enough to find a rocky world in a habitable zone? Or did we need to find a rocky world that had actually managed to retain the conditions necessary for life? The first question was relatively easy to answer with current technology. The second was almost impossibly difficult. And Kepler 186f, the planet that had been celebrated in the spring of 2014 as the first true Earth analog, was beginning to look, in the cold light of subsequent research, like a planet that had answered the first question with a clear yes, and the second question with something far more troubling. The closer the scientific community looked, the more the original promise dimmed. The second major discovery, the one that turned the conversation about Kepler 186f from concern to something closer to grim, had nothing to do with the planet itself. It had to do with a phenomenon that astronomers had known about for decades, but had not, until the late 2010s, fully understood in the context of habitability. The phenomenon was called tidal locking, and the more carefully it was studied in the years following the original announcement, the more it became clear that it was probably going to be the dominant factor shaping conditions on any planet sitting in the habitable zone of an M-dwarf. Tidal locking is what happens when a body in orbit around a much more massive body experiences gravitational forces strong enough to gradually slow its rotation until one side of the smaller body permanently faces the larger one. The Moon is the most familiar example. It is tidally locked to Earth, which is why we always see the same face of the Moon from our planet's surface. The far side of the Moon, the side that points away from us, is permanently turned away. It receives sunlight, of course, just like the near side, but from our viewpoint on Earth, we never see it. The same process that has locked the Moon to Earth also acts between planets and their stars, but it requires either a very long time, billions of years, or a very strong gravitational interaction, which means a planet that orbits very close to its star. For Sun-like stars, the habitable zone is far enough from the star that tidal locking is not really a concern. Earth, sitting comfortably in our Sun's habitable zone, rotates freely with a 24-hour day and will continue to do so for as long as the sun shines. But for M-dwarfs, the habitable zone is so much closer to the star that tidal locking becomes essentially inevitable. A planet in the habitable zone of an M-dwarf will become tidally locked within a few 100 million years of formation. Some calculations suggest the process can be even faster than that, particularly for planets in the closer orbits typical of late-type M-dwarfs. By the time Kepler 186f reached the age it is today, 4 billion years, the probability that it had retained any independent rotation was effectively zero. One hemisphere faces the star permanently. The other hemisphere faces permanent darkness. There is no day-night cycle. There are no seasons. The sun, if you stood on the planet's day side, would hang fixed at the same point in the sky forever. What does this mean for habitability? In the simplest, most intuitive sense, it means catastrophe. The day side, receiving the full energy output of the star without interruption, would heat up. The night side, receiving no energy at all, would cool down. Without an atmosphere to redistribute heat from one hemisphere to the other, the temperature difference between the two sides would be enormous, potentially hundreds of degrees. The night side would become so cold that any atmosphere present would freeze out, condensing onto the surface as solid ice. The day side, deprived of the moderating influence of an atmosphere, would become even hotter. The whole system would collapse into a state where most of the planet's volatiles, water, carbon dioxide, nitrogen, would be permanently locked in ice on the dark hemisphere, while the lit hemisphere baked under a thin or non-existent atmosphere. This worst-case scenario was first explored in detail in the early 2000s in a series of theoretical studies that examined what would happen to an Earth-like planet placed in the habitable zone of an M-dwarf. The results were stark. Without something to circulate heat around the planet, tidal locking was effectively a death sentence for habitability. The atmosphere would freeze out on the night side. The planet would, in a relatively short time, become a half-frozen, half-scorched world, with no liquid water on either hemisphere except possibly in a narrow ring near the terminator, the boundary between perpetual day and perpetual night. But the early studies, while alarming, contained an assumption that later researchers began to challenge. They assumed that the atmosphere, if any, would behave roughly like Earth's atmosphere. They modeled relatively thin, low-mass envelopes of nitrogen and oxygen with modest greenhouse contributions. What if, the next generation of researchers asked, the atmosphere were thicker? What if it were dominated by greenhouse gases like carbon dioxide, in concentrations far higher than Earth's? Could a sufficiently dense atmosphere transport heat from the day side to the night side fast enough to prevent the freeze-out scenario? The answer, when the models were run more carefully, turned out to be a qualified yes. A planet with a thick enough atmosphere, particularly one rich in carbon dioxide, could maintain reasonably uniform temperatures across both hemispheres. The atmospheric circulation would carry heat from the day side, rising in massive convective cells near the substellar point, flowing outward toward the night side, descending in cold regions of the dark hemisphere and returning at the surface. The resulting climate, while strange by Earth standards, might be habitable in a technical sense. There could be liquid water somewhere on the planet. There could be conditions stable enough for chemistry, perhaps even for life. For a few years in the early 2010s, this finding was treated as a kind of rescue for the M-dwarf habitability scenario. The pessimists had argued that tidal locking would doom these planets. The optimists could now point to the atmospheric circulation models and argue that with the right atmosphere, the doom could be avoided. This was the framework into which the Kepler 186f announcement landed in 2014. The press materials acknowledged that the planet was likely tidally locked, but emphasized that this did not necessarily preclude habitability. Atmospheric circulation could solve the problem. Liquid water might still exist. But then, as the decade wore on, the climate modeling got better. More sophisticated simulations began to incorporate effects that the earlier studies had simplified or ignored. The role of clouds, for example, turned out to be much more complicated than initially thought. On a tidally locked planet, the substellar point, the spot on the day side directly beneath the star, would become a region of intense convection. Warm, moist air would rise, cool, and form thick, persistent cloud cover. These clouds would reflect a significant fraction of the incoming stellar radiation back into space, cooling the day side below what the simpler models had predicted. The cooling would propagate around the planet, reducing the temperatures on the night side as well. In some simulations, the cloud feedback effect was strong enough to push the entire planet into a state called the snowball regime, where the surface freezes over completely and the planet enters a runaway ice age from which it cannot escape without some external intervention. There was worse to come. The newer simulations also took into account the spectral properties of M-dwarf starlight, which differs significantly from sunlight. Stars like Kepler 186 emit much more of their energy in the infrared and far less in the visible and ultraviolet. This shifted spectrum has profound implications for ice and snow on a planet's surface. Ice is highly reflective in visible light, which is why snow looks so bright on Earth. But ice is much less reflective in infrared light, which means that ice on a planet orbiting an M-dwarf actually absorbs more of the incoming radiation than ice on Earth would. The implication, when worked through the climate models, was that ice on an M-dwarf planet would melt more easily than the simple snowball calculations had suggested. This sounded, at first, like good news. Easier melting meant less likelihood of a permanent ice cover. But it also meant that the climate of such a planet would be inherently unstable, oscillating between warm and cold regimes in ways that Earth, with its much more reflective ice, simply does not experience. Long-term climate stability, the kind of stability that life on Earth has enjoyed for billions of years, might be very difficult to achieve on a tidally locked M-dwarf planet. And without long-term stability, the development of complex life becomes correspondingly more difficult to imagine. The third major piece of evidence emerged from a direction no one had been watching particularly closely, and it concerned not Kepler 186f individually, but the entire class of planets to which it belongs. As the catalogue of M-dwarf habitable zone planets grew through the late 2010s, with each new discovery briefly celebrated and then absorbed into the ongoing analysis, a pattern began to emerge in the data. It was a statistical pattern, not immediately obvious from any single discovery, but visible when you stepped back and looked at the population of M-dwarf planets as a whole. And what it suggested was that something fundamental about how these planetary systems formed was different from how our own solar system had formed, in ways that had implications no one had fully appreciated when Kepler 186f was first announced. The pattern was this. M-dwarfs tend to host multiple small planets clustered relatively close to the star, often in tight, compact arrangements with the inner planets orbiting in resonance with each other. The most famous example, discovered in 2017, was the TRAPPIST-1 system, a small M-dwarf about 40 light-years away that turned out to have 7 Earth-sized planets, 3 of them in the habitable zone, all of them packed into orbits closer to their star than Mercury is to our Sun. The TRAPPIST-1 discovery had electrified the scientific community for the same reasons the Kepler 186 discovery had 3 years earlier. Here were rocky, Earth-sized worlds in habitable zones, 3 of them around a single star, ripe for atmospheric characterization with the upcoming James Webb Space Telescope. The TRAPPIST-1 planets were the next great hope for finding signs of life beyond Earth. But TRAPPIST-1 was also a system that had been studied much more carefully than Kepler 186, in part because it was so much closer to us, and in part because all 7 planets transited their star, allowing for an extraordinary depth of follow-up observation. And as the studies of TRAPPIST-1 accumulated, they revealed things about M-dwarf habitable zone planets that had not been obvious from the more distant systems. The TRAPPIST-1 planets were small. They were rocky, they were in the habitable zone, but they were also, in several crucial respects, fundamentally different from Earth in ways that had nothing to do with their size or their orbital distance. The first difference was density. When astronomers measured the masses and radii of the TRAPPIST-1 planets with sufficient precision, they discovered that the planets were systematically less dense than Earth, significantly less dense. The implication was that the planets contained much more water, or more accurately, much more of the volatile compounds collectively called water ice than Earth does. By some estimates, the TRAPPIST-1 planets are 5 to 10% water by mass. Earth, for comparison, is about 1/10 of 1% water by mass. The TRAPPIST-1 planets are not rocky planets with oceans. They are ocean planets with rocky cores, worlds where the water layer is so thick that it extends downward for tens or hundreds of kilometers, terminating in exotic high-pressure ice phases that have no analog on Earth. This finding was generalized cautiously to other M-dwarf systems. The exact composition of the Kepler 186 planets was not directly measurable because they were too far away and their masses had never been precisely determined. But the formation models that explained TRAPPIST-1 suggested that M-dwarf systems in general should produce volatile-rich planets, simply because the conditions in the protoplanetary disks around M-dwarfs favor the inclusion of more ice in the building blocks of small worlds. The same processes that built the TRAPPIST-1 planets had probably built the Kepler 186 planets, including Kepler 186f, which meant that Kepler 186f was probably not just a slightly colder, slightly different version of Earth. It was probably a fundamentally different kind of world, one with a far thicker water layer than Earth has ever had, with a surface and an interior that bore little resemblance to anything in our own solar system. A world like this, even if it could maintain a habitable temperature, would face challenges that Earth has never faced. The deep water layer would isolate the rocky core from the surface, cutting off the chemical exchange between the interior and the ocean that geochemists believe is essential for the maintenance of long-term planetary habitability. On Earth, volcanic activity continuously replenishes nutrients in the ocean, allowing life to thrive in places where it would otherwise have no access to the trace elements it needs. The carbon cycle, which regulates Earth's climate over geological timescales by exchanging carbon dioxide between the atmosphere and the rocky interior through volcanism and weathering, would not function in the same way on an ocean world with no exposed continental crust. The whole system of feedbacks that has kept Earth habitable for billions of years would, on such a planet, be replaced by a different system whose properties no one yet fully understood. Some researchers, looking at these findings, began to argue that the entire framework of habitable zone analysis as it had been practiced through the early 2010s needed to be revised. The habitable zone, they suggested, was a useful first cut, but it was not sufficient on its own. A planet in the habitable zone of an M-dwarf, even if it was the right size and at the right distance from its star, might be uninhabitable for reasons that had nothing to do with temperature or stellar flux. Its composition might be wrong. Its formation history might have endowed it with too much water or too little, or with an interior structure that did not support the kind of geological cycles necessary for long-term stability. The question of whether a planet was habitable, in other words, could not be answered just by knowing where it was. You also needed to know what it was made of, and how it had been put together, and what its star had done to it during the first billion years of its life. And for Kepler 186f, the answers to those questions were almost entirely unknown, and likely to remain so for the foreseeable future. This was, in some ways, the deepest cut. Because the original announcement had implicitly assumed that finding an Earth-sized planet in a habitable zone was sufficient to identify a potential Earth twin. The press materials had emphasized the size match and the orbital position. They had downplayed the other parameters, partly because those parameters were unknown, and partly because emphasizing them would have undermined the central narrative of the discovery. But by the late 2010s, the field was beginning to acknowledge openly that the original framing had been overconfident. Kepler 186f was Earth-sized, yes. It was in the habitable zone of its star, yes. But that did not make it Earth's twin in any meaningful sense. It made it a small, rocky world about which almost nothing else was known, sitting in an environment that, for a variety of independent reasons, seemed increasingly unlikely to support conditions resembling those on our own planet. The discoveries kept accumulating, and the pattern they formed was unmistakable. Each new study, each new model, each new follow-up observation seemed to chip away at another piece of the original story. The size was reasonable but uncertain. The orbital position was technically habitable, but marginally so. The host star's pre-main sequence phase had probably stripped the atmosphere. Tidal locking had likely produced a climate fundamentally different from Earth's. The planet's composition was probably water-rich in ways that complicated long-term habitability. Any one of these issues, taken on its own, might have been survivable. The Earth's twin label might have weathered the loss of any single one of these assumptions. But taken together, all of them at once, the original picture of Kepler 186f had become almost unrecognizable, and the worst was still to come. The fourth discovery, the one that turned what had been a slow erosion of confidence into something approaching a quiet reckoning, came from the most unexpected direction. It did not come from new observations of Kepler 186 itself, which remained as dim and as far away as ever, accessible only to the largest telescopes on Earth. It came instead from a completely different field of research, one that had been developing in parallel with exoplanet science, but had only recently begun to intersect with it in serious ways. The field was astrobiology, and the specific question being asked was deceptively simple. What kinds of stars, in our actual galaxy, in the actual conditions that exist around them, have probably given rise to life? The traditional approach to this question had been to start with the assumption that life requires conditions similar to those on Earth, and then to look for places where those conditions might exist. The habitable zone concept emerged from this approach. So did the focus on rocky planets, on liquid water, on stars that produced enough but not too much energy for surface chemistry to operate at the temperatures life needs. But beginning in the late 2010s, a different approach began to gain traction. Instead of starting from Earth and asking where conditions resembled Earth, some researchers started from the universe and asked where the actual chemistry of life, the chemistry that we know operates on our planet, could have plausibly gotten started. The answer, when worked through carefully, turned out to depend critically on something the habitable zone framework had largely ignored. It depended on the chemistry of prebiotic synthesis. The chemistry, in other words, of how the first organic molecules necessary for life are formed from simpler ingredients. On Earth, this chemistry is thought to have begun in environments where ultraviolet light from the sun broke apart simple molecules in the atmosphere and on the surface, producing reactive fragments that could then recombine into more complex compounds. The exact pathways are still debated, but a central role for ultraviolet radiation at specific wavelengths and intensities has emerged as a likely common feature of most plausible scenarios. Without enough ultraviolet light, the chemistry simply does not start. The complex organic compounds that life needs, things like nucleotides and amino acids, cannot form in sufficient quantities, and the whole process of prebiotic evolution stalls before it can even begin. This finding had been emerging gradually through the work of researchers at the University of Cambridge and at Harvard University, among other places, and it culminated in a series of papers published in 2018 and 2019 that laid out the implications explicitly. M-dwarf habitable zone planets, the researchers argued, almost certainly received too little of the right kind of ultraviolet radiation to support the prebiotic chemistry that had given rise to life on Earth. The reason had to do with the spectral properties of M-dwarf starlight. M-dwarfs emit most of their energy in the infrared, with very little in the visible and even less in the ultraviolet. The specific wavelengths required to drive the chemistry of nucleotide synthesis, which lie in the near-ultraviolet, are emitted by M-dwarfs at intensities orders of magnitude lower than what a sun-like star produces. A planet in the habitable zone of an M-dwarf might have liquid water on its surface, might have an atmosphere, might have all the right physical conditions for life, as we know it to exist, and yet might never produce life in the first place, because the chemistry necessary to bootstrap it was missing the fundamental energy source it needed. This was a different kind of problem than the ones that had been raised previously. The earlier concerns about atmospheric stripping and tidal locking and water content, had all been about whether a planet could maintain habitable conditions over time. The prebiotic chemistry argument was about something else entirely. It was about whether life could ever have started in the first place. A planet that maintained perfectly stable temperatures and a perfectly Earth-like atmosphere and a perfect ocean of liquid water might still be sterile forever, simply because the chemistry to start life had never been able to operate. The Cambridge researchers had even calculated, with some precision, where the abiogenesis zone, as they called it, fell for different types of stars. The abiogenesis zone was defined as the range of distances from a star at which both liquid water and sufficient ultraviolet radiation for prebiotic chemistry could coexist. For Sun-like stars, the abiogenesis zone overlapped substantially with the traditional habitable zone. Earth sat comfortably within both. But for M-dwarfs, the situation was different. The abiogenesis zone for an M-dwarf, if it existed at all, was located much closer to the star than the habitable zone. So close, in fact, that any planet in the abiogenesis zone of an M-dwarf would receive too much energy to maintain liquid water on its surface. The two zones did not overlap. For most M-dwarfs, there was no place where a planet could simultaneously have liquid water and the right ultraviolet conditions for life to begin. When this analysis was applied to Kepler 186, the conclusion was unambiguous. Kepler 186f was nowhere near the abiogenesis zone. The planet received too little ultraviolet light, by a factor of more than 100, to support the chemistry that had likely produced life on Earth. Even if every other obstacle to habitability had been overcome, even if the atmosphere had survived, even if the tidal locking had been managed by atmospheric circulation, even if the water content was just right, the planet was still missing the spark that life on Earth had needed to begin. Whatever else Kepler 186f might be, it was almost certainly not a place where life, as we understand it, had arisen independently. There were, of course, caveats. The Cambridge researchers had been careful to note that their analysis assumed the chemistry of life on other worlds would resemble the chemistry of life on Earth. If alternative biochemistries existed, ones that did not require ultraviolet radiation to bootstrap, then the abiogenesis zone concept might not apply. It was also possible that other energy sources, such as lightning, hydrothermal vents, or impacts by organic-rich asteroids, could provide the necessary chemistry through pathways the researchers had not considered. The argument was probabilistic, not deterministic. It said that life was unlikely on M-dwarf habitable zone planets, not that it was impossible. But the word unlikely, in this context, was doing a lot of work. The combined weight of all the previous problems, when added to the abiogenesis zone argument, made it very difficult to construct a scenario in which Kepler 186f would actually be inhabited. For the public, none of this registered with anything like the impact of the original announcement. There was no press conference reversing the Earth's twin label. There was no NASA briefing acknowledging that the planet was probably uninhabited and uninhabitable. There were only the journal papers, dense with equations and citations, accumulating quietly in the literature, building toward a consensus that almost no one outside the field would ever read or hear about. The public continued to encounter Kepler 186f, when they encountered it at all, through the lens of the 2014 announcement. The most cosmically Earth-like planet ever found, a sibling world, a place where life might exist. Inside the field, the conversation had moved on. The next generation of researchers was thinking less about M-dwarf habitable zone planets and more about how to find Earth-sized planets around Sun-like stars, planets where the abiogenesis zone and the habitable zone would actually coincide. Telescopes were being designed for the specific purpose of imaging such planets, of measuring their atmospheres, of searching them for the signatures of life. Kepler 186f, the planet that had launched the dream, was being quietly left behind. And the most shocking finding of all, the one that would force even the most cautious researchers to confront just how badly the original story had been told, was still ahead. The discovery that would ultimately serve as the climax of this story, the one that reframed everything that had come before, arrived not as a single announcement, but as the slow integration of several independent lines of evidence over the course of 2022 and 2023. By that point, the James Webb Space Telescope had finally begun operations, and the exoplanet community was turning its full attention to the planets that had been discovered in the previous decade. The TRAPPIST-1 system was the immediate priority, partly because it was so much closer to Earth than most M-dwarf systems, and partly because its 7 transiting planets offered an unparalleled opportunity to characterize atmospheres in detail. Kepler 186f was not on the immediate observation schedule. It was too far away, its star was too dim, and the planet's transit signal was too shallow for atmospheric characterization to be feasible with current instruments. But what the Webb telescope learned from TRAPPIST-1 was going to apply, by extension, to every M-dwarf habitable zone planet ever discovered, including the one that had once been called Earth's twin. The first major Webb results from the TRAPPIST-1 system came in the spring of 2023, and they were not what most of the optimists had been hoping to see. The first planet to be observed in detail, TRAPPIST-1b, was the innermost planet in the system, sitting just inside the habitable zone in a slightly hotter orbit. Webb measured its thermal emission, looking for the infrared signature of an atmosphere. What it found was almost nothing. The planet appeared to be a bare rock, with no detectable atmosphere of any kind. The thermal emission measurements were consistent with a surface that was being heated by direct stellar radiation and radiating that heat into space without any intervening atmospheric layer to trap it. The planet, in other words, looked like an oversized Mercury, a scorched, airless ball of rock orbiting close to its star, stripped of whatever atmosphere it had once possessed. The TRAPPIST-1b result was not, by itself, conclusive evidence that all M-dwarf planets lacked atmospheres. The innermost planet in any system would be the most vulnerable to atmospheric stripping, simply because it received the most stellar radiation. Planets further out, in the habitable zone proper, might have fared better, but the result was a warning. The most pessimistic predictions of what the M-dwarf environment would do to a planetary atmosphere were being confirmed by direct observation. The TRAPPIST-1b atmosphere, if it had ever existed, was gone, and the team responsible for the observations had been careful to note that this was the first real test of the atmospheric stripping models, and the models had predicted exactly what Webb had found. Over the following months, observations of the other TRAPPIST-1 planets began to accumulate. TRAPPIST-1c, the second planet out, also showed signs of being airless or nearly so. The thermal emission measurements were less definitive than they had been for TRAPPIST-1b, but they were not consistent with the kind of thick, dense, greenhouse-rich atmosphere that the optimistic habitability models had assumed. The habitable zone planets, TRAPPIST-1e, F, and G, were harder to characterize directly because they were further from their star and therefore cooler and dimmer in the infrared. Definitive atmospheric measurements of those planets remained out of reach, even for Webb. But the trend was clear. The inner planets of the TRAPPIST-1 system did not have atmospheres. The simplest explanation, the one most consistent with the data, was that the violent early activity of the star had stripped them away, and there was no obvious reason to expect the outer planets, which had presumably been subjected to the same conditions during the same pre-main sequence phase, to have fared dramatically better. For Kepler 186f, the implications were immediate and difficult to deny. The planet orbited a star very similar to TRAPPIST-1, slightly larger, but in the same general class. It had been formed under similar conditions. It had experienced a similar early stellar environment. It had been bombarded by similar levels of ultraviolet and X-ray radiation during its host star's prolonged youth. If the TRAPPIST-1 inner planets had lost their atmospheres, there was every reason to think Kepler 186f had lost its atmosphere too. And without an atmosphere, the planet could not maintain liquid water on its surface, could not support the kind of climate that the Earth's twin narrative had implicitly promised, could not be habitable in any meaningful sense. But the deeper revelation, the one that fundamentally reframed the story, was not just about Kepler 186f It was about the entire 15 years of M-dwarf habitable zone research that had culminated in the Earth's twin announcement. Because what the Webb observations of TRAPPIST-1 were demonstrating, with hard empirical data instead of theoretical models, was that the optimistic case for M-dwarf habitability had been built on a foundation that simply did not hold up to direct observation. The models had said that thick atmospheres might survive the early stellar bombardment. The observations were showing that they had not. The models had said that some M-dwarf planets might retain habitable conditions. The observations were showing that the planets we could actually study did not. This was the shock that quietly rippled through the field in 2023 and 2024. It was not announced in a press conference. There was no formal moment of acknowledgement, but the tone of the published literature changed. Papers that would have been written with cautious optimism in 2017 were now being written with cautious pessimism. Research groups that had spent their careers searching for life around M-dwarfs began to shift their focus. The next major NASA mission planning, the Habitable Worlds Observatory, was being explicitly designed to target sun-like stars, not M-dwarfs, because the field had collectively concluded, without ever quite saying so out loud, that the M-dwarf habitable zone strategy had not worked. And in the middle of all of this, Kepler 186f sat where it had always sat, 500 light-years away, orbiting its small red star, completing one revolution every 130 days. The planet itself had not changed. What had changed was our understanding of it. In 2014, it had been Earth's twin, a sibling world, the closest thing to a second home humanity had ever found. By 2023, it was something else. A small rocky world in a habitable zone, yes, but probably stripped of its atmosphere by its star's violent youth, probably tidally locked into a climate with no stable analogue on Earth, probably too cold and too dimly lit by ultraviolet to have ever produced the chemistry of life, probably too poor in geological cycles to maintain long-term habitability even if life had somehow begun. The Earth's twin label, when you laid all the evidence on the table together, had become almost embarrassing to repeat. What made this the climax of the story, what made it the moment that reframes everything, was not just that the original picture had been wrong. It was that the original picture had been wrong in ways the field had quietly known about, at some level, even at the time of the announcement. The caveats had been there in the original paper. The concerns about M-dwarf habitability had been raised in the literature for years before 2014. The reasons to doubt the Earth's twin framing had existed from the beginning. They had simply been crowded out by the institutional incentives that favored exciting announcements over careful qualifications, by the press cycle that rewarded simple stories over complicated ones, by the genuine human desire, even among scientists, to believe that we had finally found a second Earth. The shock of the Webb results was not that they revealed something new. The shock was that they revealed how much had been quietly obvious all along. The implications of what had been learned about Kepler 186f and about M-dwarf habitability more broadly extended far beyond the fate of a single planet 500 light-years away. They forced a wholesale reconsideration of how the field of exoplanet science had been operating, what its actual results meant, and what could be learned about life in the universe from the data we had so painstakingly collected. The reckoning that began in the early 2020s was not just about Kepler 186f, it was about the entire intellectual edifice that had been constructed around the search for habitable worlds, and about which parts of that edifice could still be defended once the foundations had been examined more carefully. The first thing to fall, or at least to be quietly demoted, was the habitable zone concept itself. Not the underlying physics, which remained sound, but the privileged status the concept had been given in the public framing of exoplanet discoveries. For most of the previous decade, finding a planet in the habitable zone of a star had been treated, in press releases and educational materials, as nearly synonymous with finding a potentially habitable planet. The habitable zone had become a kind of certifying label granted to a planet on the basis of its size and orbital position, after which everything else, the atmosphere, the composition, the star's activity history, the geological context, was treated as a secondary detail. By the mid-2020s, this framing was no longer tenable. The habitable zone was a useful concept, but it was a necessary condition for habitability, not a sufficient one. A planet could sit in the middle of the habitable zone of its star and still be uninhabitable for any number of reasons, as Kepler 186f had demonstrated. The certifying label, in other words, had certified far less than people had thought. The second thing to fall was a particular kind of optimism about the abundance of habitable worlds in the galaxy. Throughout the 2010s, popular accounts of exoplanet research had often featured staggering numbers. Tens of billions of habitable planets in the Milky Way alone, a potentially habitable world around every other star. The galaxy as a vast garden of Earth-like environments, most of which we had simply not yet looked at carefully enough to characterize. These numbers had been derived by extrapolating the Kepler statistics on small planets in habitable zones, multiplied by the total number of stars in the galaxy, and treating the result as an estimate of the number of potentially life-bearing worlds. The math was straightforward. The conceptual problem was that almost all of those tens of billions of planets were assumed to be around M-dwarfs, simply because M-dwarfs were the dominant stellar population. If M-dwarf habitable zone planets were not actually habitable in any meaningful sense, as the evidence was now suggesting, then the estimates of habitable worlds in the galaxy had to be revised downward by a factor of 10 or more. The galaxy was not a garden. It might still contain habitable worlds, but they were rarer, harder to find, and concentrated around the smaller population of sun-like stars, where the technical challenges of detection and characterization were correspondingly greater. This was a sobering revision, and it was one that the field absorbed slowly and unevenly. Some researchers continued to defend the optimistic case for M-dwarf habitability, arguing that the Webb results were preliminary, that the worst-case interpretations might be wrong, that there were still scenarios in which planets like Kepler 186f could harbor life. Others took the opposite position, arguing that the field needed to acknowledge openly that the M-dwarf strategy had largely failed and that resources should be redirected accordingly. The truth, as so often in science, was probably somewhere in the middle. Not every M-dwarf planet was certainly uninhabitable. Not every result was definitive, but the burden of proof had shifted. In 2014, the default assumption had been that an Earth-sized planet in the habitable zone of an M-dwarf was probably habitable until proven otherwise. By 2025, the default assumption had become the reverse. Such a planet was probably uninhabitable until proven otherwise, and the kind of proof that would change the default in the other direction was very difficult to come by with current technology. The third thing that had to be reconsidered was the entire methodology of habitability assessment. For decades, the field had relied on a relatively simple set of criteria: size, orbital position, host star type. If a planet checked all three boxes within reasonable tolerances, it was considered potentially habitable. But the experience of the previous decade had shown that this framework was inadequate. Habitability turned out to depend on parameters that were much harder to measure than size and orbital position. The composition of the planet, the history of its formation, the activity history of its star, the presence or absence of a strong magnetic field, the thickness and composition of any atmosphere, the presence of moons that might stabilize the planet's rotation axis, the frequency of large impacts during the late heavy bombardment. Each of these factors could potentially make the difference between a habitable world and an uninhabitable one, and none of them could be measured directly for any planet outside our solar system using current techniques. The implication was uncomfortable. The field had been searching for habitable planets for 30 years, had announced dozens of candidates, had built entire research programs around the assumption that habitability could be assessed from a distance using observable parameters. But the most important factors for habitability, the ones that actually determined whether a planet was alive or dead, were precisely the factors that could not be measured from a distance. To know whether a planet was truly habitable, you would have to go there, or at the very least, you would have to obtain spectroscopic measurements of its atmosphere of a precision that was, for most planets, decades away from being achievable. The dream of identifying habitable worlds from light-year distances, the dream that had powered exoplanet science since its inception, was running into a fundamental limit. The light we received from these planets simply did not contain enough information to answer the question we most wanted answered. This limitation began to shape the next generation of space mission planning. The Habitable Worlds Observatory, NASA's planned successor to Webb, was being designed with this limitation in mind. Instead of trying to characterize as many planets as possible, the new mission would focus on a small number of nearby sun-like stars, attempting to obtain the kind of detailed atmospheric measurements that could actually answer questions about habitability. The strategy was a deliberate shift away from the breadth of Kepler toward depth. Fewer planets, but characterized in much greater detail. The hope was that by focusing resources on the most promising targets, planets where habitability was at least plausible on first principles, the field could make real progress on the central question of whether life existed elsewhere. But the strategy was also an acknowledgement of how much the field had learned from the failure of the broad survey approach. Kepler had taught us that planets were common. It had not taught us, despite the enormous effort that had gone into it, that habitable planets were common. That second question was going to require different methods, different missions, and probably different decades. There was something humbling about all of this, and the more honest researchers were willing to say so out loud. The exoplanet community had spent 30 years constructing increasingly sophisticated theoretical and observational frameworks for identifying habitable worlds, and the result of those 30 years was the gradual realization that we did not yet know how to identify habitable worlds. We knew how to identify planets. We could measure their sizes and orbits with extraordinary precision. We could even, in some cases, get hints about their atmospheres. But the leap from those measurements to a confident statement about habitability had turned out to be far longer than anyone had anticipated. Kepler 186f was the most visible example of that gap, the planet that had taught the field, the hard way, just how much we still did not know about what made a world a home. Stepping back from the technical details for a moment, it is worth asking what the story of Kepler 186f actually means for those of us who are not professional astronomers, for the people who follow these discoveries from a distance and try to make sense of what they tell us about our place in the universe. Because the implications of what happened with this planet, of what was promised and then quietly retracted, are not just about exoplanet science. They reach into much deeper questions about how humanity processes information about the cosmos, how we form pictures of our cosmic neighborhood, and what we should reasonably expect from the search for life beyond Earth. The first lesson, and perhaps the most important one, is that the universe is not obligated to provide us with the answers we want. This sounds obvious when stated plainly, but the entire arc of the Kepler 186 story suggests that we have not really absorbed this lesson, either as a culture or as a scientific community. For 30 years, the field of exoplanet science has been driven by the implicit assumption that the discoveries would eventually arrive on a timeline that matched human attention spans. We would launch a telescope. It would find planets. Some of those planets would be habitable. Some of those habitable planets would have life. The story would unfold year by year, with new headlines marking new milestones in a progression that led inexorably toward the answer to the most important question we have ever asked. Is there life elsewhere in the universe? But the universe does not deliver its answers on this schedule. The questions we are asking turn out to be far harder than the questions we know how to answer. The technology we have developed turns out to be far less powerful than what we would need to actually resolve those questions. The patience required to wait for genuine answers turns out to be measured in decades or centuries, not in news cycles or grant periods or the careers of individual researchers. The Kepler 186f announcement, in this light, looks less like a milestone in a steady march toward understanding and more like a kind of premature celebration, a moment when we mistook the discovery of a small rocky planet in the right orbital position for the discovery of something far more meaningful. The mistake was understandable. The pressure to deliver exciting results, to justify the investment in space missions, to maintain public interest in deep questions whose answers might take generations to arrive, is enormous. But the mistake was still a mistake, and one that the field is now having to acknowledge openly. The second lesson is about what it means to be on a habitable planet at all. One of the strange side effects of the Kepler 186 story and of the broader research into M-dwarf habitability that surrounded it is that it has gradually revealed just how unusual and how precarious our own planet's habitability actually is. Earth is not just a rocky planet in a habitable zone. Earth is the result of an extraordinarily long chain of fortunate circumstances, each of which had to fall within narrow tolerances for the world we inhabit to be the world we inhabit. Our Sun is a relatively rare type of star, large enough to provide stable energy for billions of years without going through the violent youth that characterizes M-dwarfs. Our orbital position is in a sweet spot of the habitable zone, neither too hot nor too cold, with sufficient stability that liquid water has persisted continuously on the surface for nearly all of the planet's history. Our axial tilt has produced seasonal variation that drives ecological diversity without creating climate extremes that would prevent the development of complex life. Our moon, large for a planet of our size, stabilizes that axial tilt against gravitational perturbations from other planets in the solar system. Our atmosphere has been actively regulated by the carbon cycle, which depends on plate tectonics, which depends on the planet's interior heat and water content, which depend in turn on the conditions of its formation. Our magnetic field, generated by a still active iron core, shields us from cosmic radiation and the solar wind. Our planet sits at the right distance from the galactic center to avoid the dense radiation environments closer in, but close enough to have access to the metallic elements produced by previous generations of stars. Each of these factors is essential. Each of them depends on circumstances that, when you look across the full diversity of planetary systems in the galaxy, turn out to be the exception rather than the rule. What Kepler 186f has helped to teach us, almost as a side effect of its own habitability problems, is that Earth is not a representative example of what a habitable planet looks like in the universe. It is something closer to an outlier, a configuration that requires many things to go right in many independent dimensions, and that consequently appears, on the evidence available so far, to be rarer than the early optimism of exoplanet science had suggested. This is not necessarily a depressing conclusion. It can also be read as a deeply humbling one, a recognition that our planet is something precious and unusual, the product of a long and intricate history that has produced conditions found nowhere else in our cosmic neighborhood and possibly nowhere else for thousands of light years around us in any direction. The third lesson, related to the first two but standing on its own, has to do with what we should reasonably expect from the search for life beyond Earth in the coming decades. The Kepler 186 story suggests that the timeline most people implicitly assumed for this search, the timeline that imagined unambiguous discoveries arriving every few years, has not been realistic. The actual timeline, the one that emerges from a careful look at what the field has and has not been able to learn over the past 30 years, is much longer. It is possible that the first confident detection of life on a planet beyond Earth will happen sometime in the next 20 or 30 years if the right missions are funded and the right techniques mature on schedule. It is also possible that such a detection will take longer than that it will require multiple generations of telescopes and refinements of technique, that it will arrive not as a single headline, but as the gradual accumulation of evidence over decades. And it is possible, although this is the possibility no one likes to talk about, that life beyond Earth might be rare enough that we will not detect it in any of our lifetimes, that the answer to the question of whether we are alone in the universe will not be available to anyone reading this story or watching this video, that it will be a question for our descendants or their descendants to finally resolve. This is, I think, the most important thing the Kepler 186 story has to teach us. It is not that the planet itself turned out to be different from what was advertised. It is that the entire enterprise of searching for life beyond Earth is harder, slower, and more uncertain than the publicity around individual discoveries has often suggested. There is no shame in this. Hard questions take time. The question of whether life exists elsewhere in the universe is perhaps the hardest question humans have ever asked, and we have only been seriously trying to answer it for a few decades, with instruments that, despite their impressive capabilities, are still in some sense the very first generation of tools we have built for the purpose. The fact that we have not yet found the answer is not a failure. It is a reflection of how genuinely difficult the question is. And the fact that some of the early candidates, including Kepler 186f, have turned out to be less promising than they initially appeared, is not evidence that the search is hopeless. It is evidence that the search is real, that the discoveries are subject to genuine verification, and that the universe is not going to be fooled by our enthusiasm. We will get to the answer when we get to it. And the journey, with all its corrections and revisions and unexpected turns, is part of how science actually works. There are questions about Kepler 186f that remain genuinely open, even now, even after a decade of follow-up research and the slow accumulation of evidence that has reshaped our understanding of the planet. Some of these questions might be answered in the coming years, with the missions and instruments that are already planned or already under construction. Others might remain unanswered for a much longer time, for technical reasons that have to do with the specific challenges of studying a small, dim, distant world. It is worth spending some time on what we still do not know, because the unknowns are themselves a kind of story, a map of where the field is heading and what the next generation of researchers is going to have to confront. The most basic unknown, the one that has been hanging over the entire discussion, is whether Kepler 186f actually has an atmosphere at all. The evidence from the TRAPPIST-1 system, particularly the bare rock results for the inner planets, suggests strongly that the habitable zone planets of M-dwarfs are likely to be atmosphereless or nearly so. But suggestion is not proof. The James Webb Space Telescope, despite its extraordinary capabilities, cannot directly measure the atmosphere of Kepler 186f. The planet is too far away, its star is too dim, and the transit signal is too shallow for the kind of detailed spectroscopy that has been performed on closer, brighter systems. We can extrapolate from TRAPPIST-1 and from the theoretical models, but we cannot, with current technology, look at Kepler 186f and see for ourselves whether it has retained any of its original atmospheric mass. That measurement is going to require either a much larger space telescope, of the kind being considered for the Habitable Worlds Observatory and its successors, or a direct imaging mission designed specifically for the characterization of exoplanet atmospheres at large distances. Neither of those capabilities will be available for at least another decade, and possibly longer. The second open question concerns the planet's surface, which we have effectively no information about at all. Is it covered in ice? Is it bare rock? Does it have continents and oceans, or just a global frozen surface? Are there signs of past volcanic activity, evidence of plate tectonics, traces of weathering by liquid water from some earlier and warmer phase of the planet's history? These questions, which would be answerable for a planet in our own solar system with a single visiting spacecraft, are essentially unanswerable for Kepler 186f with any technology that exists today or that is likely to exist for many decades to come. To map the surface of a planet 500 light-years away in any meaningful sense, you would need an interferometric telescope array spread across vast distances in space, an instrument that would dwarf even the most ambitious mission concepts currently under discussion. Such a telescope might eventually be built, but the timeline for it stretches into the late 21st century at the earliest. The third open question, and the one that has perhaps the most direct relevance to the question of habitability, concerns the planet's interior. We do not know whether Kepler 186f has an iron core like Earth, or whether it has a smaller core or no core at all. We do not know whether it generates an internal magnetic field, which would provide some protection against the stellar wind and slow the rate of atmospheric loss. We do not know whether it has tectonic activity, which on Earth is essential for the long-term regulation of climate through the carbon cycle. These questions about planetary interiors are extraordinarily difficult even for the planets in our own solar system. We have spent decades sending probes to Mars and Venus and the gas giants, and our understanding of their interiors remains incomplete even with all that direct exploration. For a planet around another star, we are essentially blind to its interior, with only theoretical models to guide our expectations. And the models, as the Kepler 186 story has made clear, can be wrong in ways that take a long time to become apparent. There are also unanswered questions about the planet's history that may never be resolvable. Was there ever a period, perhaps early in the planet's life, when conditions on its surface were genuinely habitable? Did it experience a brief window of warm, wet conditions before the atmospheric stripping took its toll? Are there geological features that would record such a history, ancient riverbeds, or lake basins, or chemical signatures of past water activity? These kinds of questions have been answered for Mars, where we now have strong evidence that liquid water flowed on the surface billions of years ago before the planet's atmosphere was lost. But Mars is in our solar system. We have sent rovers there. We can examine its rocks directly. For Kepler 186f, the equivalent investigation is simply not possible, and may never be possible within any reasonable extension of current technology. What is possible, what the field is actively working toward, is a much more comprehensive understanding of M-dwarf habitable zone planets in general, even if not specifically of Kepler 186f. The TRAPPIST-1 observations are continuing, with more planets being characterized and more sophisticated atmospheric models being tested against the data. Other nearby M-dwarf systems, such as the Proxima Centauri system and the Teegarden star system, are being studied with ground-based telescopes equipped with extreme adaptive optics, which can in some cases obtain direct measurements of nearby planets that transit-based methods cannot. The extremely large telescope, currently under construction in Chile and scheduled for first light later this decade, will dramatically expand the range of M-dwarf planets that can be studied in detail. Each new observation, each new measurement, builds up the statistical understanding of what M-dwarf habitable zone planets are really like, and what the planet called Earth's twin probably resembles by extension. Beyond ground-based observations and the current generation of space telescopes, several major missions are in various stages of planning and development that will eventually provide much more direct constraints on the kinds of questions that the Kepler 186 story has raised. The Nancy Grace Roman Space Telescope, scheduled for launch later this decade, will conduct a wide-field microlensing survey that will detect planets across an enormous range of orbital distances, including in the cool outer regions where information about planetary system architectures is currently sparse. The European Space Agency's Plato mission, also planned for later this decade, will search for Earth-sized planets around bright, sun-like stars, the kind of targets that will be far easier to follow up than the dim, distant Kepler targets that have dominated the catalogue for the past decade. And the Habitable Worlds Observatory, NASA's flagship mission concept for the 2040s, will be designed specifically to image and characterize potentially habitable planets around sun-like stars within a few tens of light years of Earth. None of these missions will, by themselves, tell us what Kepler 186f is really like. But together, they will tell us what worlds like Kepler 186f are really like, by sampling enough planets in enough detail to develop a robust empirical picture of how habitable zone planets actually behave around different types of stars. And from that picture, the questions about Kepler 186f and its uncertain fate will eventually find their answers, even if those answers arrive long after the original announcement has faded from public memory. There is something worth pausing to consider, here near the end of this story, that goes deeper than the specifics of any single planet or any single research program. It has to do with what it actually means to be looking outward into the universe in this particular moment of human history, and what the experience of Kepler 186f with all its corrections and revisions and quietly walkback claims, ultimately tells us about our place in the cosmos. For most of human existence, the night sky was a kind of fixed and decorative ceiling. The stars were arranged in patterns that did not change from one generation to the next. The constellations our distant ancestors named are the same constellations we name today. The brightness of the brightest stars, the colors of the most prominent ones, the positions of the planets that wander through the zodiac, all of it has remained essentially constant over the entire span of recorded history. Stand outside on a clear night in any era, from ancient Mesopotamia to medieval Europe to the early industrial cities of the 19th century, was to see almost exactly the same sky. The universe felt, in some deep way, like a permanent backdrop, a stage on which the dramas of human life played out without affecting or being affected by it in any meaningful sense. That picture began to change, slowly at first, and then with accelerating speed, beginning in the 17th century. Galileo's telescope showed that the moon had mountains, that Jupiter had moons of its own, that the Milky Way was not a band of cloudy light, but an unimaginable multitude of individual stars. In the 18th century, William Herschel discovered that what looked like single stars were sometimes binary systems, and that the galaxy itself had a structure. In the 19th century, spectroscopy revealed that the stars were not different in kind from our own sun, but were composed of the same elements, burning by the same fundamental processes. In the 20th century, Edwin Hubble showed that the universe was full of other galaxies, and that those galaxies were rushing away from each other in an expansion that traced back to a single moment of origin nearly 14 billion years in the past. Each step expanded the universe we knew. Each step diminished, in a certain sense, the importance of any single planet, any single star, any single galaxy in the vastness of what was being revealed. The discovery of exoplanets, beginning in 1995 and accelerating through the early decades of the 21st century, has been the latest, and in some ways the most personal of these expansions. It is one thing to know that there are billions of galaxies, each containing billions of stars. It is another thing entirely to know that around those stars, in numbers we are only beginning to understand, are actual planets. Real worlds with real surfaces and real skies and real, if often forbidding, conditions. The Milky Way, on the evidence accumulated over the past 3 decades, contains at least as many planets as it does stars, and probably significantly more. Most of those planets will never be named, never be visited, never be examined by any human or human-built instrument with enough precision to learn anything substantive about them. But they are there, by the hundreds of billions, distributed across a galaxy that is itself only one among hundreds of billions of others. The cosmic neighborhood that we used to imagine as a backdrop has turned out to be a community, populated by uncounted worlds whose existence is now established as scientific fact rather than philosophical speculation. The story of Kepler 186f is, in this larger context, a kind of microcosm of the entire human encounter with the exoplanetary universe. We found a planet. We were excited. We thought briefly that we had found something close to home. The closer we looked, the stranger and more alien the planet revealed itself to be. The Earth's twin label gave way, gradually, to something more honest, the recognition that this was not a sibling world, but a world of its own kind, shaped by its own history, subject to its own conditions, no more obligated to resemble Earth than any of the billions of other worlds that share its star type and its general orbital geometry. The planet did not change. Our understanding of it did. And in the process of revising our understanding, we learn not just about this specific planet, but about the limits of our methods, the gaps in our knowledge, and the ways in which our expectations had been shaped more by our hopes than by what the universe actually contains. There is, I think, something to be said for sitting with that experience rather than rushing past it. The fact that Kepler 186f turned out not to be Earth's twin does not make it less interesting. If anything, it makes the planet more interesting, because it forces us to confront the actual diversity of the cosmos rather than the simplified version we had been hoping to find. Here is a world that may have no atmosphere, that may have once had one and lost it, that is locked in permanent rotation with one face perpetually turned toward its sun, and the other perpetually turned away. Here is a world that, even if it has retained some atmosphere through processes we do not fully understand, exists in a climate regime with no analogue anywhere in our own solar system. Here is a world whose surface, if we could ever see it, would be utterly unlike anything in human experience, a place where the sun would be smaller and dimmer and redder than ours, where the sky would be a different color, where the very wavelengths of light reaching the ground would not include the components our biology has evolved to use. To call such a place a twin of Earth was always a stretch. To recognize that it is something else entirely is not a failure of the discovery. It is an expansion of what we mean by the word planet, an acknowledgement that the variety of worlds in the universe extends far beyond the categories we have inherited from our own solar system. This is, in the end, what the search for exoplanets has been teaching us. Not that the galaxy is full of Earths waiting to be found. Not that life is common, or that habitable conditions are easy to achieve, or that the cosmos is a friendly place that welcomes biology with open arms. The lessons are quieter and more humbling than that. The galaxy is full of worlds, yes, but those worlds are remarkably varied, often strange by human standards, and only rarely organized in configurations that resemble our own. The conditions that produced Earth and the life on it appear to be rare, the product of a long chain of contingencies that did not have to turn out the way they did. The universe is not against life, but it is not for life either. It is indifferent, vast, and structured by physical laws that do not care whether the planets they produce are habitable or sterile. Out of that indifference, life has arisen at least once, on at least one planet, around at least one star. Whether it has arisen anywhere else, whether the conditions for it exist on planets we can study from a distance, whether we will ever be able to confirm its presence on a world other than our own, remains the great open question. The answer, when it comes, will probably take longer than any of us expect. And the journey to that answer will probably contain many more moments like the one we have just lived through. Moments when an apparent discovery turns out to be more complicated than it first seemed, when our expectations have to be revised, when the universe quietly insists on being itself rather than what we wanted it to be. So where does this leave us? At the end of the story of Kepler 186f, it leaves us with a planet that still exists, that still orbits its small red star 500 light years away, that still completes one revolution every 130 days, as it has done for billions of years, and will continue to do for billions more. The planet itself has not been diminished by anything that has been discovered about it. It is no less real now than it was on the day of its announcement. The light from its star still travels across the immense distance between us, carrying the information we have used to study it, indifferent to the labels we have applied to it and then revised. In a very literal sense, nothing about Kepler 186f has changed in the past decade. Only our understanding has changed. Only the story we tell about it has been rewritten. And that, perhaps, is the most honest place to end, because the story of Kepler 186f is, above all else, a story about how human knowledge actually advances. It does not advance by the steady accumulation of confirmed facts, building toward an ever clearer picture of reality. It advances by claim and counterclaim, by initial discovery and subsequent revision, by the slow correction of overconfident first impressions through the patient work of follow-up observation and theoretical refinement. The Earth's twin label, applied in the spring of 2014, was not a lie. It was an honest expression of what the available evidence at the time seemed to suggest, filtered through the natural human tendency to interpret ambiguous data in the most exciting possible way. The slow walking back of that label in the years that followed was also not a failure. It was the scientific process working as it is supposed to work, with researchers continuing to ask questions, run new analyses, and update their conclusions in light of new evidence. The story, when you tell it honestly, is not a story of mistakes corrected. It is a story of understanding deepened. What has emerged from that decade of deepening understanding is a picture of Kepler 186f that is, in some ways, more interesting than the picture we started with. The Earth's twin, taken at face value, was a comforting image. A world like our own, with conditions like our own, where life like ours might plausibly exist. That image, while exciting, was also limiting. It treated the planet as a stand-in for Earth rather than as a thing in itself. The revised picture, the one that has emerged from years of careful follow-up, is more difficult to summarize in a single phrase. It is a picture of a world that may once have had an atmosphere and lost it, that orbits a star whose violent youth shaped its history in ways we are only beginning to understand, that is locked into a rotation pattern with no Earth analogue, that sits in a habitable zone that may not be habitable at all when other factors are properly accounted for. It is a picture of a strange world, in other words, a world that requires us to expand our conception of what a planet can be rather than fitting it into categories we already understood. And in expanding our conception, the planet teaches us more than a simple Earth analogue ever could have. There is a kind of beauty in this, I think, if you are willing to see it. The universe does not have to give us what we want. It does not have to organize itself around our hopes for what we will find when we look outward. It is allowed to be its own thing, structured by its own logic, populated by worlds that owe us nothing. When we go out looking for second Earths and find instead the strange and various worlds that actually exist, we are not being denied something. We are being shown something. The actual diversity of planetary systems, the actual range of outcomes that physics permits, the actual conditions that prevail on the most common kinds of worlds around the most common kinds of stars. These are valuable things to know, even when the answers they provide are not the ones we had been hopping for. They are valuable because they are true. Kepler 186f, in this sense, is one of the most valuable discoveries of the past decade, not in spite of how the story has turned out, but because of it. The planet has done what the best scientific discoveries always do. It has changed the questions we know how to ask. It has revealed assumptions in our thinking that we did not know we were making. It has redirected the field toward more careful methods, more honest framings, more realistic expectations about what we will and will not be able to learn from the next generation of observations. Future discoveries will be reported with more caution because of what happened with Kepler 186f. Future missions will be designed with more attention to the questions that this planet has raised. Future researchers will work in a field that is more humble and more rigorous than the field that announced an Earth twin in April of 2014. All of this is gain, even if some of it is gain that came at the price of giving up a story we had wanted to be true. There is one more thing worth saying, because it is the thing that the story keeps returning to and that I think gives it whatever larger meaning it might have. We are alive, on this planet, in this particular moment of cosmic history, at a time when humanity is for the first time looking outward with instruments capable of seeing what is actually out there. No previous generation has had this. No previous generation has known that the planets around other stars exist, that they number in the hundreds of billions across our galaxy alone, that they can be studied and named and catalogued and slowly understood. Whatever else we say about the present moment in human history, we should at least say this. We are alive in the age when humanity first lifted its eyes from its own ground and saw, with real eyes and real instruments, the worlds beyond. That is something extraordinary. That is something none of our ancestors had. It will be true for the rest of human history, however long that history turns out to be, that the first generations to look outward with clear vision were ours. The story of Kepler 186f is part of that looking. It is part of what we learned, and what we got wrong, and what we corrected in the early years of an enterprise that will continue for as long as humans continue to wonder what else exists out there. The planet itself will go on, indifferent to our changing interpretations, orbiting its dim red star in a corner of the Cygnus constellation, doing what it has done for billions of years before anyone on Earth knew it existed, and what it will continue to do for billions of years more. We will not visit it. Our great-grandchildren will not visit it. The planet belongs to a future so distant we cannot meaningfully imagine the civilization that might one day, if any civilization ever does, lay eyes on it directly. For now, all we have is the light. And the light, when we read it carefully, when we resist the temptation to read it more eagerly than it deserves, tells us things about the universe that we could not have learned any other way. So look up tonight. Find the constellation Cygnus if you are in the northern hemisphere and the season is right. Kepler 186 is somewhere up there, too dim for your eyes to see, far too distant for any telescope you are likely to ever look through to reveal it as anything other than a point of light. But it is there. And around it, somewhere in the slow dance of its small planetary system, the world that was once called Earth's twin is also there, going about its strange and uncertain existence, a reminder that the universe is full of worlds, that most of those worlds will not look like home, and that the journey to understand them is only just beginning. If this story has stayed with you, take a moment to like the video, to subscribe if you have not already, and to share it with someone who looks up at the night sky and wonders what is out there. The cosmos is vast, and the search continues, and we are only at the beginning of what humanity will eventually learn. Thank you for listening. Keep looking up. The next discovery is already on its way.